Graphing absolute value functions. We'll start with vocabulary. Absolute value is the distance of a number from 0. The absolute value of -3 equals 3. The absolute value of 5 equals 5. A parent function is the simplest of a particular type of function. The vertex is the maximum or minimum value of a function. Axis of symmetry is the vertical line that acts as a mirror of the function. The slope is the steepness of a line, or the rate of change. And a translation is a horizontal or vertical slide. We'll be using all of these terms in this video. The first example says graph the absolute value parent function f of x equals the absolute value of x. Notice we started with a table of values that center around 0 in the x column. So those x values are our domain or our input. We want to input each x into the function. So we want to consider f of -2. The absolute value of -2 is 2. F of -1 equals the absolute value of -1. That's 1. F of 0 equals the absolute value of 0, which is 0. F of 1 is 1, and f of 2 is 2. So now we're going to plot these points on the coordinate plane, and we'll notice that we have two pieces of linear functions that come together at that vertex, which is 0, 0. This is the absolute value parent function. Notice its vertex is 0, 0, and it opens up. It has slopes of -1 and 1 with the two respective pieces. So the rest of this video will be graphing versions of this parent function and seeing how it compares to this one. Graph f of x equals the absolute value of x minus 2. So we'll start with the table of values, and we'll think about each x value as we substitute it into the function. The absolute value of -3 is 3, and 3 minus 2 is 1. The absolute value of -2 is 2. 2 minus 2 is 0. The absolute value of -1 is 1. 1 minus 2 is -1. Absolute value of 0 is 0. And 0 minus 2 is -2. The absolute value of 1 is 1. 1 minus 2 is -1. The absolute value of 2 is 2. Minus 2 is 0. Absolute value of 3 is 3. And 3 minus 2 is 1. We'll plot these points, and we'll notice that at a value, namely 0, -2, the slope changes direction from decreasing to increasing. We'll connect the points, and we'll notice our vertex is 0, -2. And we'll further notice this function, the absolute value of x minus 2, is a vertical shift 2 units down from the parent function. And we'll try to pay attention to the structure of these equations and generalize how to graph these functions by just transforming the regular parent absolute value function. All right, we'll look at another example. Here it's graphing f of x equals the absolute value of x plus 3, all inside the absolute value bars. And I'm just going to substitute in my x's. And so, for example, here's one. When I substitute -3 in place of x, I get f of -3 equals the absolute value of -3 plus 3. That's the absolute value of 0, or 0. Let's substitute -2 in place of x. Negative 2 plus 3 is 1. The absolute value of 1 is 1. We'll substitute negative 1 in place of x. Negative 1 plus 3 is 2. And the absolute value of 2 is 2. And f of 0 equals the absolute value of 0 plus 3. The absolute value of 3 is 3. And we'll plot these points. And we'll notice our vertex is that point that is the minimum value, namely negative 3, 0. And now let's notice that this equation resulted in a horizontal shift 3 units to the left of the parent function. Right, so in this next example, we're going to have a horizontal and a vertical shift. So you can make a prediction. How many units to the left or right and how many units up or down will the parent function be shifted? We can make our table of values and substitute in f of 1, the absolute value of 1 minus 4. The absolute value of negative 3 is 3, and 3 plus 1 is 4. F of 2, the absolute value of 2 minus 4. That's the absolute value of negative 2, which is 2 plus 1 is 3. And keep using mental math to evaluate the function at each x value. The absolute value of 4 minus 4, that's the absolute value of 0, plus 1 is 1. And here the graph turns, and we start increasing again. So we'll plot these points, and we'll observe our vertex is 4, 1. And we'll notice that this particular graph, the absolute value of x minus 4 plus 1 is shifted 4 units to the right and 1 unit up from the parent function. Okay, so sometimes we're going to have a number outside of the absolute value, and that's going to change how steep the curve is. So instead of the slope being 1 and negative 1, or negative 1 and 1, the slope will be multiplied, in this case, by that number 3. So f of negative 2 equals 3 times the absolute value of negative 2. That's 3 times 2, or 6. F of negative 1 is 3 times the absolute value of negative 1. That's 3 times 1, or 3. F of 0 is 0. F of 1 is 3, and f of 2 is 6. So we can plot these points, and we'll notice something interesting, that the vertex remained the same because we did not have a horizontal or a vertical shift. But this graph underwent a compression, a stretch. It was actually a shrinking, right, from the parent function, because the new function's slopes are 3 times those of the parent function slopes. So this is actually 3 times more narrow than the parent function. The vertex is the same, 0, 0, but instead of going over 1, up 1, I'm going over 1, up 3 from the vertex. All right, one last example. And here we have f of x equals negative 4 times the absolute value of x. Now this is interesting, because when we go to graph this, instead of the graph opening up, it's going to open down. And we'll try to make sense of that. It'll be the same vertex, 0, 0, right, because there was no horizontal or vertical shift. But the parent function underwent a reflection because of that -4, and the slopes are also -4 times those of the parent function slopes. So it'll be 4 times as steep. Instead of going over 1, down 1, we're going over 1, down 4.